نقدر نبتدي موضوع الالتراساوند. الساوند is formed just of waves. When these waves hits the eye, we start to hear what's going on. So if you get some vibrations, some vibrating waves coming to the eye, you start to hear. The human eye can hear up to frequency of 20 kilohertz. If you have a frequency higher than that, it will not be heard. So ultrasound means that we have a sound with a high frequency, higher than the ability of the eye to hear. In the instrument of ultrasound, we have a transducer in our hand, and this transducer receives some electrical current. It will change this electrical current into sound waves. When these waves hit a surface, waves will be reflected back to the transducer, and then the transducer will change it into electrical current. So we have an electrical current coming from the instrument to the transducer, changing it into waves. When waves hits a surface, waves reflected back to the transducer, then inside the transducer change it again into electrical currents. Inside the transducer, we have some material called piezoelectric crystals. This piezoelectric crystal get the character of changing electrical current into mechanical movement, and again mechanical movement into electrical current. Then we have, this is the eye to be examined, and this is the transducer, and this is the instrument. So electrical current, when coming back, it will pass inside the instrument to be magnified and to be displayed on a screen so we can see what's going on. Get here a small video for that. We have different frequencies of ultrasound. In the abdominal ultrasound used for examination of structures in the abdomen, we have a frequency between 1 to 5 megahertz. In the ophthalmic ultrasound, we have a frequency of 8 to 10 megahertz, or sometimes 20 megahertz. In the ultrasound by microscopy, we have a frequency from 35 to 50 to 100 megahertz. So we want to understand what's meant by the frequency and how does it affect the type of instrument we are using. You know, sound and light all is part of the huge electromagnetic spectrum. We are familiar with the the visible light, the different wavelengths, and all that we are accustomed with in the optics we usually study. And here you get this part of frequency. You get here FM radio, AM radio, TV, shortwaves radio. So it's a whole spectrum. Sound is part of that spectrum. So everything we know about light, we can apply it to the sound. Light and sound moves in waves. In this video, you notice that when wave come, the boat goes up, then comes down on its same location. This is another wave, but here this wave is a very high amplitude, very rising wave compared to the first one. So if you throw a stone in a water, waves will start to form, spreading to the outside. To describe any wave, you have three things to comment on: the height, the amplitude of the wave, the wavelength, the distance between one crest and the next crest, and the frequency. Notice this video. If this is the boat and we have waves coming, it goes up a second, a third, a fourth time. So frequency means how many waves passes at certain point in a second. So in this case, the waves get this both up and down 4 times in a second. So we'll say the frequency of this is 4 per second, or get 4 cycles per second, or 4 hertz per second. So the frequency is the number of wave crests that pass through a fixed point per second. Here, 1, 2, 3, 4, 5, 6, 7, 8, 9. So we'll say that the frequency is 9 cycles per second, or 9 hertz. So the word hertz means the number of cycles per second. 1 complete cycle per second means 1 hertz. 10 cycles per second, 10 hertz. 1,000 cycles per second, 1 kilohertz. 1 million cycles per second, 1 megahertz. What is the relation between the frequency and the resolution, meaning the quality of image, and what is the relation between the frequency and tissue penetration? If this is a table and we get so many apples thrown on the surface of this table, and we get waves getting through this table like this is a long wavelengths, or another waves with the short wavelengths. The upper row here we get a low frequency, only 4 cycles over this screen, while in the bottom you get high frequency, many cycles. The wavelength below is short, the wavelength up is high. Now imagine this is ultrasound and we get waves passing through this apple, so it will send information back to the transducer. So I will understand that there is an apple here at this location. Then on coming up, I will understand there is another apple here, another one here, another one here, and I'm going to miss the apples in between. In the lower bottom, the wavelength is short, so you get waves passing through each apple, every apple. So I'm going to send back to the instrument that I get these all apples. So in this case, I send back informations only about these 5 apples, but on the bottom row, I'm sending back so many informations for every individual apple. What does it mean? It means that when the frequency is high, I'm sending back to the instrument more and more information. So this will give me a higher resolution, a better information of things coming back to me. So resolution means the sensitivity, how much I get information. We have an axial resolution that is in the line of propagation of the waves, something in front, something behind, something more far. And we get lateral resolution. You know, waves are also not going axial, also moving from side to side. So I can get information about one apple, an apple next to it, an apple on the other side. This is a lateral resolution. While axial resolution is one apple, an apple after it, an apple behind it, and so on. So both are affected. I get a more information with high frequency, both the lateral resolution and the axial resolution. Now I want to see this video. This nice cartoon, I once got it from the TV. You notice that we get small baby in blue and a grown-up man or woman in red shoes, and they are moving together. I want you to notice the steps of these two characters. The adult get a wide steps, while the baby get a short steps. So they are both moving hand in hand. So to pass through one distance, the adult will say pass 5 or 6 steps, but the baby, because get a short movement, he will pass 20 steps to reach to the same destination. This is the actual thing what we have in all the waves. In white light, it's a mixture of red and blue. The red is the long waves and the blue is the short side. So to pass together to reach to the same location at the same time, the red will pass a long feet and the blue will pass a short feet. Now imagine this is a man walking in a muddy land. This is an adult with the big steps, so he get into this muddy land 3 times. But this is the small baby walking in the same muddy land with short steps, so he get into this muddy land 10 times to pass the same distance. So what does it mean? The amount of resistance to the movement in the bottom line is low and in the upper line is high. What does it mean? If I'm going to lose energy to continue more, this will be more prominent in the upper row. Short steps, more resistance in the media I'm passing through, I'm going to lose energy and I will not go any further. So if we have the baby with short steps and the adult with the long steps moving on the same muddy land, the baby will meet the resistance many times and he will lose energy and he cannot go on any further. He will completely be tired. While the adult will meet the resistance less and less, so he can continue more and more walking. So if you have a low frequency, you can go further, you get a higher penetration, but the resolution is low. On the other hand, if you have a high frequency, your penetration is weak. You cannot go deep in the tissues, but the resolution is high. So if you get a high frequency, waves gradually get absorbed, changed into heat, and no more energy to go deeper and deeper. This is the difference between ultrasound and UBM, ultrasound by microscopy. In ophthalmic ultrasound, we have a longer wavelengths, so the penetration is deep and deep. We can go deep up to 4 centimeters. In ultrasound by microscopy, the depth is maximum to 4 millimeters because the frequency is high and the energy is absorbed. This is as far as the penetration is considered. But when it comes to resolution, the amount of information sent back, the resolution in UBM is high. It's 40 microns between one location and another location, 40 micron to the side or to the depths, we get information. While in ultrasound, the regular ultrasound, the resolution is 9,040 microns. You get information from one location and the next one is around 9 microns apart. In UBM, it's only 40 microns apart. Even in the same instrument, you can buy a UBM with a frequency, with the handle frequency 35 or frequency 50, or even we get instruments with a frequency 100. A higher frequency means I'm going to get a better image, but the penetration will be less. And the same with the ophthalmic ultrasound. You can buy an handle with a frequency of 10 megahertz, 8 megahertz, 16 megahertz, 20 megahertz. The higher the frequency, the better the image, but the less the penetration. If you think more about the OCT, it's light. The frequency of the light is quite high and the wavelength is quite short. So the image is much, much better. This is the image of the anterior segment with the UBM, and this is the image with the OCT. Here we get a higher quality of image, but the penetration is less. OCT cannot pass through the maximum to the iris, cannot pass through the iris to show the lens, but the UBM can show the lens and the ciliary body. So it's two things. You can get a better image, a higher resolution, but you are losing the penetration. This is the resolution in case of ultrasound, UBM, and in case of OCT. The information from one location to the next location in OCT is 5 microns or 10 microns. In UBM, it's higher than that. In ultrasound, it's 900. So just if you read this information, if you can understand it, this means everything is okay with you. If you don't understand it, tell me, I can repeat what I've explained. Okay, clear? Okay. Simply in the visible lights formed of mixture of wavelengths, the short ones, the blue, and the long ones, the red. If you are examining the fundus, if you are using the red free, that is the light with no red, this has got only short waves, it get a low penetration, so it will only let you see the retina, while if you use the ordinary white light, including the red, it will go deep to the choroid. So if you use white light, you get information coming back to you from the choroid, but if you use the red-free light, you only see the retina. So whenever you want to examine a superficial lesion and you want to see it more, it's better to avoid information from deeper structure. That's why we use the red-free light for fundus examination to examine the retinal fiber layer. We don't have any information coming from the choroid. This is the same idea of waves and penetration. Now, ultrasound, if you buy an instrument, you receive these instruments with two probes. A probe, the small one on the bottom, and a B probe is the large one. A probe, we call it a time amplitude mode. This probe will send just one beam of ultrasound. This ultrasound, when it comes and meets the anterior surface of the cornea, sound will be reflected back to the transducer, and we get a peak here. Then at the posterior surface, you get another peak. Then in the EC, nothing. At the anterior surface of the lens, sound is sent back, so you get another peak. Then when sound reaches to the back surface of the lens, it will be reflected back. Then we get a third or fourth peak. Then through the vitreous, nothing is there. Then when you reach to the wall, the retina, choroid, and sclera, you get these peaks, and gradually the sound energy will be absorbed. So, A mode, we call it time amplitude mode. Time means the time factor after how many milliseconds the peak is there. This will tell me the distances between structures. If the anterior chamber is deep, then the distance between the cornea and the lens will be larger. If the lens is thick, then the distance between the anterior and posterior surface will be longer. And we know the speed of passage of light or sound, speed of passage of sound in the different structures, then we can transfer the delay in time into distances. So this mode, this A mode, will give us the length of the eye, the distances between the structures of the eye. We use this to examine, say, in biometry to determine the IOL to be implanted. We need to know the axial length of the eye. This is the first mode. The second probe, we call it the B mode, or the brightness mode, the large mode, the large probe. As you notice here, the probe here is not only sending one wave, no, it's moving, and all the time is sending different beams. So this is the one beam. Say, when it comes here, sending sound back, this will be recorded not in a form of a peak, it will be recorded in a form of a dot. If the sound wave coming is very intense, then this dot will be very bright. If the sound coming is weak, then the dot will be dim. So instead of recording things in a form of peaks, higher and low, it's recorded in a form of dot, bright or less bright. And again, when sound reaches to the next point here, it will send information recorded as dots. So different waves, when encountering different surfaces, sending information back, and the information is recorded in forms of dots. When these dots, you see it together, you see it as a form of a section in the eye. So we say this looks to be the posterior surface of the lens, this is the vitreous cavity, this is the wall behind, this is the optic nerve. Then you get a full information. So we have a probe or a scan to measure a length, and a B probe, brightness probe, to measure to see a section. So whenever you receive an instrument, you give two probes and you can use either of them. Seems we have a problem with this video. Okay, everything we know about light we can apply to the sound. We know from the optics that when light hits a surface, the surface may absorb the light completely, it's an opaque surface, or the light or part of the light is reflected back as in mirrors, or it passes through that media as in refraction in lenses. The same is applied to the sound, because both are part of the electromagnetic spectrum. We are accustomed to the term optical density in optics, and here we can say sound impedance. It depends, it will tell me how far the sound is going on. This depends on the sound velocity and the density of the media to resist the passage of sound. Now, if sound is coming to a surface and this surface is separating two media with different impedance or different sound resistance, the sound, part of it will be reflected back and the angle of incidence equal to angle of refraction, and part of the sound will pass through. The same thing we know about light, you can apply to the sound. And if there is a difference between the sound density of the two media, then everything will be changed the way we know it about light in optics. Now we get here sound coming from aqueous to the lens. At this interface you get this high peak, while if the anterior chamber is full of blood, then the resistance or the density of passage of sound is different compared to the aqueous. Then we are moving from one media to another media with smaller difference in density, then the peak will come smaller. So everything you know about optics, light, you can apply it to the sound. The amount of echoes coming to the transducer depends on different things. One thing is the gain. The gain is the amount of sound I'm sending. When I'm using the instrument, I can get a low sound or high sound. like in the TV. You can get the sound quite high to hear more, or you can get it low. So the same thing, I get a knob, I can increase the sound I'm sending, or I can reduce it. We call this a gain. Mostly we use a gain about 80, but sometimes if you want to see things more, you can rise the gain. If you want to get things less, you can lower the gain, and I can tell you after a while how we do that. The other thing is the material itself, the surface we are receiving, does it reflect sound more or not? If you get something like a foreign body, it will reflect sounds more and more, while other structures will reflect sounds less and less. So the amount of reflection coming to me depends on the nature of the surface I'm examining, and also the amount of sound I'm sending. The second thing is the energy there or the energy is lost. Let's have this example of an intraocular foreign body. We have a foreign body here that it reflects all the sound back. So there is no sound to be seen here. Nothing is reached this line. So we see it dark. We call this shadowing. When you get something reflecting everything and no more sound to pass through. This is very bright because most of the sound is reflected back, and there is no sound to let you see this area. So the sound is absorbed completely or reflected completely from this media, and nothing to visualize things behind. We call this sign shadowing, that this foreign body is throwing a shadow behind it. It's simply reflecting sound, and there is no energy to visualize things behind that foreign body. Here, this is the foreign body reflecting everything, and there is shadowing behind. This is the shadow of the optic nerve, and this is the shadowing because of this foreign body. Here there is a gain of 81 decibels. This is 81 decibel, and here the gain is 76, less sound. You notice here that everything is bright, reflections are coming back, and here everything is getting less and less dim. So if you want to visualize a foreign body, lower the gain, so everything will be less apparent, and the foreign body, because it reflects much amount of the sound, is still quite visible. This is another example. You notice here there's some points in the vitreous cavity, and we start to lower the gain, so the image is getting less and less bright, and these dots are not seen even here. So if you want to see something with the reflectability low, you increase the gain. If you have something very reflecting sounds, you lower the gain. So we don't do the examination, the whole test at the same level. We can raise the gain to show things or lower the gain to show other things. Now, if you are examining a surface and you are perpendicular to that surface, so the whole sound will be reflected back to you, and I get a very bright image. While if the sounds are coming with an angle, some of the sound will come back to you, but the other will be reflected away from you. So you will get less amplitude. Here in this example, the transducer is perpendicular to the surface to be examined, so the amplitude is high. If you get the examination coming with an angle, the amplitude is less. More angulation, less amplitude. So whenever I'm examining the posterior pole, I'm perpendicular to that pole. If I want to examine the bottom, I should come from up to examine the bottom. I should always be perpendicular to the surface I want to examine to get more and more information. Again, the surface itself, if it's irregular, the reflection coming to be back to me, I'm going to lose part of it. If it's homogeneous, the reflection is more. Now, next point is the probe orientation. This is the B probe. We get a mark. This mark tell me on display on the screen where the say the ultrasound is moving here. I'm putting the mark on the nasal side. So the probe is moving from nasal to temporal. So the upper part of the screen will show me the nasal area, and the lower part of the screen will show me the temporal area. I can apply the probe in different positions, and I can apply it in a transverse position or longitudinal position or axial position. In transverse position, I'm going to apply the probe here tangential to the limbus. Say if the mark is here up, so the ultrasound will start up, then start to move down. This will give us a transverse section in the structures. Imagine this orange is the model of the eye, and we have the cornea here, and we put our probe like this, tangential to the limbus. So the ultrasound, the mark is up here, the ultrasound will start here, up, then start gradually to move down. So on the screen, this upper part will be on this part will be in the upper part of the screen, this part will be in the middle, and this will be in the lower part of the screen. What? ايه؟ المارك هو probe وجت مارك، انا احطه زي ما انا عايز. احطه زي ما انا عايز برضه، يعني انا ممكن احطه كده يبقى المارك نيزل، يبقى انا عارف ان انا بشوف النيزل في السكرين من فوق، وممكن اعكسه احطه temporal يبقى انا عارف ان انا بشوف التمبرال فوق. بس actually we are accustomed in certain positions ان النيزل يبقى ان الدايركشن اوف ذا مارك يبقى نيزل، لكن افرض انا في شغلي عكست حطيته تمبرال، اتس اوكي، بس ابقى انا فاهم انا شايف ايه. So in this particular case, when putting a transverse section, the sound is examining the lower part. We start on the nasal side. So this is the location of the mark. Ultrasound will start on the nasal, then by time it will go here and ending on the temporal. In this example, we are putting transverse section. So this is the mark. We start on the nasal, then end to the temporal. And this is the screen. This is the nasal and ending to the temporal. So if you get this lesion, this tumor, here I am on the nasal, this is the nasal, and then the elevation, and here this is the temporal. So on this position, I'm getting information about the lateral extension of the lesion. How many hours does it extend? Say from 4 o'clock to 8 o'clock. This is the orientation we're accustomed to. If you're doing, say, putting the probe here, this is the mark to the nasal side. When I put the probe up, I'm doing photography on getting information of this part. Say I'm having information from this location to that location. The middle here is 6 o'clock. So I will say I'm making a transverse section at 6 o'clock. If I'm putting the probe here, I'm getting information on this area. So I'm saying I'm having photography of transverse section at 3 o'clock. If I'm putting the probe here, I'm getting information on 7 o'clock. So just as if we get an hour, and I'm examining an area, the middle of this area is what clock? You get me? So this is a transverse section at 6 o'clock. This is a transverse section at 9 o'clock. This is an example of transverse scan at 3 o'clock. I'm putting the mark up. I'm examining this nasal area. This is the 3 o'clock position. And the ultrasound will start here and will end here. So this will be the upper part of the screen, and this will be the lower part of the display I'm going to see in the instrument. Like this. If this is the lesion, so this is the upper here, and this is the lower here. I'm making a transverse section like this orange. I'm cutting it transversely. Transverse examination, actually, it's not all the time a dead transverse. Sometimes in the first location here, it's a real transverse. But sometimes you go a little bit backward toward the equator, or even back to the optic nerve. This is not a dead transverse, but we are accustomed to speak about it. It's a transverse section. A real transverse is that we should move our transducer here, here, and here. This is a real transverse all the time, but this is inaccessible. We're always at the limbus. So, or even we can go a little bit to the equator, but we cannot go behind that. So even if we get a little bit, not a real transverse, we describe it as transverse. Now the second position is the longitudinal. Here you notice that the probe orientation is perpendicular to the limbus. The transverse one, it was tangential. The ultrasound is tangential to the limbus. Like in here, we are perpendicular to the limbus. This will give us a longitudinal section in the eye. Here we get the mark toward the cornea, so the ultrasound will be to the opposite side on the ciliary body. Then the ultrasound will go gradually backwards toward the equator. So we are making a longitudinal section in the eye. Here I'm putting the mark toward the cornea, and the back is toward the equator. Like this, the mark is toward the limbus and the back is behind toward the equator. So if you have a lesion like this, the ultrasound will start The ultrasound will start from the ora serrata and gradually will go toward the optic nerve. And on the screen, the upper part means toward the ora serrata and the lower part means toward the optic nerve. So we are giving a section, a longitudinal section of the lesion. We can say how far this lesion is extending in an anteroposterior direction toward the ciliary body and toward the optic nerve. Here I'm putting the probe at 12 o'clock to get an image of 6 o'clock. So this is the longitudinal section of 6 o'clock. If you put the probe here, you're having an image of 7 o'clock. If you are putting the probe here, you have an image of 9 o'clock. If you're putting the probe here, you have an image of 11 o'clock. I'm getting information of the opposite meridian. This is a longitudinal section at 3 o'clock. So if you have a lesion, I will tell this lesion extends from the ora serrata to the optic nerve for how long, the distance of the anteroposterior extension of the lesion. Again, longitudinal scan can be over the ciliary body, or I can get it back longitudinal scan on the equator, or longitudinal scan toward the optic nerve, because the range of movement of the ultrasound cannot cover from the ora serrata to the nerve, so I can see it part at a time. See here, I'm putting the probe to examine the optic nerve area, and gradually we're going backwards with the probe to get information from more anterior locations. The third is the axial scan. In the first two positions, we are not examining the lens as a whole at all. We're just having the probe at the limbus. We are avoiding the lens to get more information of the posterior segment, to avoid losing some information by sound attenuation through the lens. Here in the axial scan, we are putting the probe through the cornea, through the lens. So the lens appears in our section. Like this. So in this situation, ultrasound is passing through the lens and the lens appear in our section. So in the first two positions, we don't have the lens, we avoid it. While in the axial, we get the lens. The axial can be horizontal, can be vertical, can be oblique. I can put the probe like this. This is a transverse axial. This is the vertical axial. This is an oblique axial. So this is transverse. I'm avoiding the lens. This is longitudinal. I'm avoiding the lens. But this is axial. I'm getting the image of the lens in my way. Now, this is a case of retinal detachment. We have a membrane attached to the optic nerve, and we can see the lens here. It looks like a funnel. And this is a transverse section of the same case, and we can see the retina as a circle. This is a closed funnel retinal detachment in an axial section and in transverse section. If this is the retina, and this is the attachment of the retina of the optic nerve, transverse section, you will end like this. While axial section, you will have that appearance. So this is the same tent. It means you cut it transversely, it will appear as an oval or circle. Or you cut it axial or longitudinal, it will appear as a funnel. We've all passed through this, nothing new. So we have transverse section, longitudinal section, and axial section through the cornea. Transverse, avoiding the lens, but we are tangential to the limbus. Longitudinal, avoiding the lens, but we are perpendicular to the limbus. Axial, we are through the lens.